Hello and welcome to the Differential Equations unit in AP Calculus. So the word differential equation just sounds so fancy and complicated, but as we'll see, it's really not that bad. In fact, in my opinion, this is one of the easiest units because you've already learned a lot of the stuff we're gonna learn in Algebra 2. But the second half of this video on logistic growth and Euler's method, that's only on the BC test, so yeah. Let's start with separable differential equations. By the name, we're going to have to separate it so we have y's on one side and x's on the other side. For example, here, we can rearrange it to get y dy equals 2x dx, and then we're going to integrate both sides, since we have the dy and the dx already here, to get y squared over 2 is equal to x squared plus c. When we're solving for y and multiply by 2, we'll get y squared is equal to 2x squared plus c. It's not a 2c because a constant times 2 is still a constant. C is just the arbitrary constant. Finally, we'll take the square root and get y is equal to plus or minus square root of 2x squared plus c. And then to solve for c, we have this 0.46 here. Since y is positive, we know it's going to be the positive root. So we're going to get 6 is equal to the square root of 2 times 4 squared is 16 plus c. 6 is equal to square root of 32 plus c. And we can square both sides. 36 is equal to 32 plus c. So c is equal to 4. And putting that back into our original equation, we'll get our final answer, which is y is equal to the square root of 2x squared plus 4. Yeah? Okay. This was a pretty simple example, but the steps for all of them are going to be the same. Split it, integrate it, and solve it for c. However, some equations are not separable at all. The most obvious example being dy dx equals x plus y. You just can't separate this no matter what. Just one more quick thing before I move on. If I have a differential equation like this one, following the steps I just said, you'd get y is equal to e to the negative 1 over x plus c plus 4. By the properties of exponents, we can split the exponent up to get y is equal to e to the c, e to the negative 1 over x plus 4. And since e to the c is just a constant to a constant, this e to the c is just going to be another constant. So I can replace the e to the c with just a plain c, giving y is equal to c e to the negative 1 over x plus 4. Then if you're given an initial point, you could plug that in and solve for c. Next we have exponential growth and decay. For a graph like this one, we can see that the derivative changes with respect to y. I can write this as dy dt, this is the t and this is the y, where k equals ky, where k is the proportionality constant. If we solve this equation for y, we'd get y equals y initial e to the kt, and y initial is the initial value for y when t is equal to 0. These two equations are what you're going to use to solve these types of problems. You'll be given some of these quantities and asked to solve for the other ones. For example, you might be given the initial condition, and you might be given a point t comma y, and use that in this equation to solve for k. And if you solve for k and you need to use that k value in a different part of the problem, make sure not to round it. The best way to keep it exact is to store the k value as a variable in your calculator. If you don't know how, I'll show you right now. So, say we wanted to store the number 3 in the variable a. The way I do that is I'd press 3, and then I'd press store, and then if I wanted to store it as a, I'll press alpha, and there's a little green a there, so I'll press a, and then press enter, and that's it. Now I can use a instead of 3 whenever I want. So I can do like a plus 2, and it'll give me like that. Okay. If you're in AB, you're done. If you're in BC though, let's keep on going. So we know in real life, stuff doesn't keep going up forever. It's going to look more like this graph, where it goes up for a bit, and then slows down and levels off. Now, I'm making this in April of 2020, and there's a thing going on in the world that you maybe possibly have heard of that makes this kind of graph extremely relevant. But anyways, let's define some variables. P is the population. K is still the proportionality constant. And m is the carrying capacity. You may remember carrying capacity from biology class. It's the maximum population that can be supported. And looking at this graph, it's clear that the derivative is greatest, that the population is increasing quickest at half of the carrying capacity. Anyway, so we'll take our equation from the previous slide, dp dt equals ky, and then we're going to add this thing, 1 minus p over m, to account for the carrying capacity. If we solve this equation for p, we're going to get p equals m over 1 plus a e to the negative kt. A here is another constant, which unlike k has an equation of its own. You can solve for a as the carrying capacity minus the initial population, should be a p, yeah? Initial population, divided by the initial population. So once you get the equations, with these three equations down, it's just the same thing as before. You're given equations, you're given values, you use these equations, plug them in, and then you'll get your answers. Okay, finally we have Euler's method. This is kind of like local linear approximation in that we're using the slope of a tangent line as an approximation. This is used mainly for differential equations that can't be separated. The idea of this is that we're taking the slope of a point, using that as an approximation, then taking the new slope, and then just rinsing and repeating until you get the answer you want. Obviously, the smaller your delta x is, the better the approximation is. The same thing as in when we did local linear approximation. So the way I was taught it was using this table, and it's a really simple way. The best way to explain this is with an example, right? Say we're given the point 2, 3 as we're given here, and the differential equation dy dx is 2x minus y, and we're asked to approximate 1.5. We're approximating y when x is 1.5 by using the Euler's method with 5 equal steps. So we'll start by writing down the given point here. So we're given 2, 3. Use the differential equation now to find the slope at that point. So at this point, it's going to be 2 times 2 minus 3, which is 1. And then, since we're starting at x equals 2, and we want to approximate x equals 1.5. Whoa, what's going on? I don't know what's going on there. Each step is going to be negative 0.1. Right, the step size. What the hell? Negative 0.1. So we're going to use that in the third column. Our slope is 1. Our step size is negative 0.1. So our slope times our step size is negative 0.1. And then finally, since we have our original y value here, and then our m delta x here, we're going to add these two. So 3 plus negative 0.1, that's 3 minus 0.1, or 2.9. Okay, so you're going to keep doing this over and over, and then, so this is going to be our next point, and we keep doing this over and over, just rinse and repeat, until you get 1.5 comma whatever. In this case we have 1.5 comma 2.61051. Don't round your y value anytime during this process. As you can see, it's been kept as like the actual number the whole time. After you do a couple of these, it's just going to be really easy and you don't really have to think about it too much. Anyway, so we're done. That was a pretty short one. I hope you found this helpful and enjoyed it, and I'll see you next time.